Hi, welcome back. This is our last lesson in Unit 8 of Algebra 2. This lesson is called Graphs, Complex Zeros, and something fundamental about polynomials. So I'd like us to start with a graphing utility window I've got set up that you can follow along, and we're just going to graph the functions y equals x all the way up through y equals x to the sixth. So without further ado, let's go ahead and bring that up here. I'll bring up Desmos. And we're going to use a x-axis is going to be -3 to 3. And you can do this along with me using Desmos or a graphing calculator if you have one. Or you can just kind of copy what I put up there. -10 to 10. Also by ones. Okay. That looks pretty good. So that looks pretty much like what you have on your paper. Oh, I didn't mean to open that. All right. But we're going to graph y equals x squared. Okay, so you can see that that should be the shape that you're expecting. You can see that, and I want you to focus on what happens as we pick a point at the center and kind of move off to the right or left, and see how we go up in both sides. Let's take a look at y equals x to the third. So this is x cubed, and this is a function that we want to be fairly familiar with the shape of this function. Okay, it's one of our kind of important ones to know. And you can see that this x cubed function makes this kind of S shape here. And the right-hand side goes up, rather similar to the parabola y equals x squared, but the left-hand side goes back down. And that's because these negative numbers are not being squared, they're being cubed. And negative numbers cubed remain negative. Let's take a look at x to the fourth. Okay, this again looks more like that y equals x squared, but look how flat it is. It's not really a parabola, it's almost like a capital U shape, but you see it going up and down on both sides. Let's change this back to the fifth, and you'll notice that it just went down again. Okay, we'll take it back to the sixth. Now it's going up again. In fact, let's make a slider. And we can, I can do some settings on this slider here. We're going to step by 1 from 1 to 20. And look as I go through even powers, they are pointing upwards. And as I go to odd powers, they point downwards. And the shape just gets flatter and flatter between -1 and 1. That's kind of the effect that it has. But the left-hand side is kind of alternating. So when the power is even, both sides point upwards. When it's odd, one side points down, the other side points up. And that's kind of a big concept that I want you to have in front of you, okay? So let's just quickly sketch these if you haven't already. All right, y equals x. You know, that was something like this. X squared was something like this. X cubed began this kind of shape like that. But then x to the fourth moved back into this kind of flat U shape. X to the fifth became even more flat, but also still S-shaped. And then x to the sixth, we're getting closer and closer to that kind of sharp turn right there at 1. Okay, so how does the end behavior, that meaning the far left and far right side of the graph of polynomials of even degree compared to that of odd degree? What we're going to say is that even degree polynomials go up on both sides. And that's because when the leading coefficient is positive. Whereas in odd degree, they're opposite. So I want you to think even, I want you to think this, odd, I want you to think that. So the degree of the polynomial, we remember this, the degree of the polynomial of a polynomial function of x is the highest exponent on x. The leading coefficient is simply the coefficient, that number in front of the highest degree term. And it's called the leading coefficient because if we write it in standard form, the highest degree term should be first, so it should be the leading one. So the leading coefficient test, the end behavior of a polynomial depends only on the degree of the polynomial and the leading coefficient. So I say end behavior because what's happening near this y-axis in the middle, we don't know. We don't know this area here. I don't know there. But I do know that if it's a positive graph, then the even degrees are going to end up being like a parabola opening up and up. But an odd degree is going to go down on the negative side and up on the positive side. Now, if we have a negative leading coefficient, these ends just flip. The left now goes up and the right goes down. And then, of course, even degree, both sides go down here. Okay. So let's take a look at some practice problems. Without using a calculator, could we match each graph with its equation based on the leading coefficient test? Okay, so let's talk about A. That's a negative 2x cubed. So if it's an x cubed, then I know that this graph is going to be going in opposite directions on the left and the right. It's going to be going, one side's going to be going down, the other side going up. But because the leading coefficient is negative, that tells me that the graph is falling to the right. So I need to be this graph here because the negative 2 as the leading coefficient tells me that we're falling to the right. Anytime your leading coefficient is negative, you have to fall to the right. Because it's an odd degree, I go in the other direction on that side. All right, let's do g of x equals x to the fifth minus 3x cubed. So odd degree, leading coefficient is positive. So this one. All right, let's take a look at this one. The highest exponent is 4, and again, the only one left is this one. We know that when it's an even degree, both sides go in the same direction. This will be up and up because it's a positive leading coefficient. All right, let's try a practice problem. I want you to match each of these equations to one of these three graphs. Okay, hopefully you didn't have any trouble with that. The x to the fifth graph needs to be going up to the right and down and to the left, so that's x to the fifth. This here is negative x to the fourth graph because it's going down on the left and right. And then, looks like we had a couple of positive ones. I may have been a little quick to say this was x to the fifth. Maybe you thought this one down here was x to the fifth. Well, this could go with A, but if I have to pick, this would go with it because it's got a y-intercept of negative 5. You see that? And this has got a y-intercept of positive 1. So that's one other piece of information you can use to help you distinguish. That's it. Another issue, though, is that while this could have been an x to the fifth graph, this can't be x cubed because an x cubed can't have more than 2 turning points. 1, 2, 3. But I didn't want to talk about that issue today, but I did want you to think about using the y-intercept to help you. Okay, the real zeros of a polynomial are located on the x-axis of the graph. We know that. We know that real zeros are x-intercepts. Practice 7.2. True or false? An odd degree polynomial must have at least one real zero. True or false? Answer that question best you can. An odd degree polynomial must have at least one real zero. Well, I hope you agree that that's true. That's true because because the two end behaviors go in different directions. So the two end behaviors go in opposite directions. We've seen some pretty curvy looking graphs, but if it's an odd degree, it must go something like that or something like that. It has to go up or down forever. An even degree polynomial must have at least one real zero. No, that is false. We have seen polynomials, quadratic, which is even degree, not have a real zero. because they both sides of the polynomial point in the same direction. I'll let you write that down. Most all branches of mathematics have one theorem that is so important it is called fundamental. You're now ready to learn that theorem for algebra. We won't be proving the fundamental theorem of algebra. The proof of it is quite challenging and well beyond the scope of this class, but we can use it. We know that a polynomial of degree n has exactly n complex zeros. That's what the fundamental theorem of algebra says. Now, with theorems in math, you need to be careful not to overstretch it. This theorem says that the polynomial of degree n will have n complex zeros, but it does not say that they'll all be unique. They could be the same zero multiple times. And it also doesn't say that they're all real. It says they're complex. So let's take a look at some different examples, and we'll see some of the special cases. All right, given the polynomial function f of x equals x cubed minus 5x squared plus 3x plus 9. According to the fundamental theorem of algebra, how many zeros must we have? I notice I said non-distinct and complex, so they could be repeated, they could be imaginary. The answer is 3. This has 3 zeros because the degree of the polynomial f is 3. Let's find all of them. Notice we're using complex zeros here, so we're going to have to use our imaginary numbers again for this lesson. If you need help remembering how to handle imaginary numbers, go back and look at Unit 6. So I am going to look and see if I can group this. Unfortunately, I cannot. So I'm going to have to guess rational zeros. My rational zeros will be numbers that divide 9. So I'm going to start with just a positive 1. All right. 1 times negative 4 is negative 4. So that makes that negative 1, and then that makes that negative 1, and then that makes that 8. Okay, so that turns out that was not, looks like that one did not work. So let's try another one. Let's try negative 1. Negative 1 also divides 9. So 1, negative 5, 3, and 9. So negative 1 is negative 6, and then that would make that 6 plus 3 is 9. That makes that negative 9 and 0. All right, cool. So we know that negative 1 is a 0 and x plus 1 is a factor. So I can rewrite f of x, which I'll start by saying is equal to 0, because I'm solving equal to 0. X plus 1 times, and remember this was x cubed, so after I divide it by something at degree 1, I get x squared. So at 1x squared minus 6x plus 9. And then this I can factor further as x minus 3 squared. And I usually like to write it that way to emphasize something, but I want to show you a little bit different way of saying that. X minus 3 squared I could also say is x minus 3 times x minus 3. So it looks as if we get a 0 at negative 1 and at 3, but what we'll sometimes see people comment is that we got 3 2 times. We got 3 with a multiplicity of 2, that we got it twice. So does my result from part B match part A? Part B told me that my zeros were negative 1 and 3. Well, the naive answer would be to say no. I was told by the fundamental theorem of calculus I would get 3 zeros and only got 2. The sophisticated answer is that I did get 3 zeros. It's just one of them was repeated. So I would say yes. We got x equals negative 1. And x equals 3 twice, which is 3 zeros. They're not distinct, but they're 3 zeros. All right, let's try another one. Okay, this one here, we can solve this one. First we'll answer this question. How many zeros does the fundamental theorem of algebra claim that we will have? It says we'll have 4, because that is the degree. Of f. Well, this one here is in what's called quadratic form. So I'm going to factor it by using x squared and x squared. And then something that multiplies to 36 and subtracts to 5 is 9 and 4. So I'll say negative 9 and plus 4. This I can factor further as x minus 3, x plus 3. But the other one I cannot because it's not x squared minus 4, it's x squared plus 4. Then I'll set each one of these factors equal to 0 and solve. This is easy. That just tells me x equals 3 and x equals negative 3. This over here, if I subtract the 4 over, I have to use square roots, and we use plus or minus when I take a square root of both sides. But remember that the square root of a negative number is imaginary. So this is actually plus or minus 2i. So negative 2i and positive 2i. So what all are our zeros? Our zeros are 3 and negative 3, negative 2i, and 2i. We're not going to spend a lot of time on complex zeros. I just bring it back up again to demonstrate the fundamental theorem of calculus. It said we'd have 4 zeros. We got 4 zeros. It's just that 2 of them are imaginary. Okay, so hopefully you've taken time, pause the video to try this. Let's go over it. Okay, according to the fundamental theorem of calculus, we know this should have 3 zeros because of the degree. Let's find all the zeros. Is this groupable? I don't believe so. So the possible rational zeros would be the plus or minus 1, plus or minus 5. But also because we have this 2 here, we have to consider numbers that denominators, fractions, 1/2 and plus or minus 5/2. Because remember, the denominator of your fraction can divide this first number. So we have a little bit to try. Let's just get to it. 2, negative 9, 14, and negative 5. And I'm not... I'm actually kind of thinking 1 might work. When I check it in my head, it looks like it does. So I'm going to go ahead and go with that. And 7... No, that didn't work, did it? Okay. So I'm just going to erase those. Let's see here. Let's try a negative 1. So I get 2, and then that would be a negative 2, and that's a negative 11. And then this would be a positive 11. Okay, that's getting worse. All right, let's try 5. So 2 times 5 is 10. That's 1. Make that 5. Nope. Okay, let's try negative 5. So negative 10, negative 19. That's way out of here. All right, so the next one I'm going to try is 1/2. So bring down the 2. 1/2 times 2 is 1, and then that makes that a negative 8, which makes this a negative 4, which makes this a 10, which makes this a 5. So it's a 0. All right. So we can rewrite f of x as being x minus 1/2 times 2x, now it goes down to a squared, minus 8x plus 10. Now, one of the things here, though, with this x minus a 1/2 is that anytime that happens, we have x minus a fraction here, there's going to be a GCF in the other side. And you can actually pull this GCF out and distribute it to here. So I'm actually going to pull out a 2 from here and put it over here, making this 2x minus 1. And then this becomes x squared minus 4x plus 5. Let's see here. This definitely looks factorable. Well, is it? No, it's not factorable. Never mind. It looked like it, but it's not. So this gives me x equals 1/2. We already knew that, but we'll have to use the quadratic formula for this. So that becomes 4 plus or minus the square root of 20. Ooh, not 20. 16 minus 20 is negative 4. So this is 4 plus or minus 2i over 2. So it's 2 plus or minus I. So our zeros are 1/2, 2 plus I, and 2 minus I. So does it match part A? It sure does. We did get 3 zeros, even though 2 of them were imaginary. What I'd like you to consider is applying this property to the x cubed plus 8. The naive solutionists think this has only 1 0 at -2, but in reality, we can get we can get 2 more zeros that are complex using our sum of 2 cubes factoring pattern. So I'll leave that to you to ponder, and I'll see you in the next unit.